Okay, so let's begin. So what have we done up to now? So last 3 lectures we spent, first we defined what it means for cycles to intersect properly. Then we gave a formula for intersection multiplicities. Then we checked that things that are expected by intuition are true. By that I mean if the intersection is transversal along a component of the intersection scheme, then the intersection multiplicity is indeed 1. And then in yesterday's lecture, we saw a moving lemma which gives a well-defined product at the level of Chow groups. Okay, so it says that given any 2 cycles, you can move one so that it intersects properly. And also, if one of the cycles is rationally equivalent to 0, then you can move then the intersection product is also rationally equivalent to 0. But these proofs were very tricky. So just to set up this fact, it took a lot of work, right? Geometrically, you saw. But we did not make any progress towards various compatibilities or functorialities of this intersection product. Okay, so because since the construction is ad hoc, it makes it difficult to work with. So we only handled the so-called basic moving lemma. So the strong moving lemma, what was it supposed to do? It was supposed to so given 2 varieties, the intersection class was supposed to be supported on the Chow groups of the intersection. Okay, and so that the class that we expect was supposed to be the push forward of that inside the ambient scheme. Okay, so our moving lemma, etc., did not give anything of that sort. Okay, and anyway, at the time when Fulton and Macpherson came up with this theory, developed this theory, the proof of that fact was not there, or the proofs in literature had some gaps and so on. And still at this point there is no correct proof of that fact, no direct correct proof of that fact. Okay, so so last week you have spent a lot of time setting up the machinery of Chern classes, Segre classes, and so on and so forth. Now is the time to put it to use and see how this functorial and compatible intersection product can be defined using what we did in the last week. Okay, so I indicated a definition in my first lecture. There was a little bit of sloppiness involved there, so I will just correct that, and then we can start with the. So today's lecture is to give you an overview of the Fulton-Macpherson intersection product. Okay, so note that the case of arbitrary, so if you take 2 closed subvarieties of an ambient variety and suppose that the ambient variety is smooth, so then the case of intersection of these 2 was reduced to the intersection of their product with the diagonal, which is a regular embedding. Okay, and for such things it's good to have one of the things regularly embedded inside the ambient variety, because then the normal bundle equals the normal cone, and then it gives you a way to so the deformation techniques that you saw in the lectures of Chetan. So let I from X to Y be a regular embedding of codimension B. Okay, and let nxy be the normal bundle of normal bundle of this immersion. Okay, and so the setting is that F is any morphism from V to Y. So in particular, it could be inclusion of a subvariety. But anyway, I will indicate why taking any morphism is important in Fulton's theory. It makes lots of computations easy, or reduces it to known easier computations. Okay, and we'll just assume that all our schemes are equidimensional. Okay, or pure dimensional. I'll not keep on writing that. Okay, so define W by the pullback square. So the pullback of this diagram. So there are two maps to y, I and f, and you form the pullback. Okay. So now, so since this I is a regular embedding, you have the cone, which is a vector bundle on X. So this agrees with the normal bundle. So here I'm being a little sloppy. I mean in the sense that I mean the underlying scheme of the vector bundle, of the normal bundle. And yeah, so there is also the cone of W inside V, but the left diagram need not be pullback. Also, I is a regular embedding does not mean that this is a regular embedding. Okay, so one has to be a little careful. But the formula that I gave in the last lecture actually works, but one has to see where the intersection is taken. That's where it's a bit of a yeah, this thing. Okay, so now you have this normal bundle of X inside Y. You can pull it back to W. Okay, so let me call this map G. Okay, so let N be the pullback of this. So this is a vector bundle on W. Okay, and let okay, so let okay, so let pi into W be the projection. Okay, so now I want to know how are the bundles N and the cone of W inside V related. Okay, so suppose I is the ideal sheaf of X in Y. So and let J be the ideal sheaf of W inside V. Okay, so now I want to ask how, so what is the ideal sheaf of so okay, so how are these ideal sheaves I and J related? Just from the fact that this is a pullback diagram. Or in other words, so of course you to compare two ideal sheaves, they first should be on the same scheme, right? So what is the relation? So I is an ideal sheaf here, J is here. So what is the relation between F upper star of I and J? This is the question. Okay, so can somebody answer? Yeah? Yeah? So what we want to say is that if you pull back this ideal sheaf I, then it will generate J, correct? Okay, so in other words, if you take the okay, so now so we are obviously interested in the cones, right? So what we will do, we will look at F upper star of I to the n modulo I to the n plus 1 to this. So now this map is surjective, right? And what does this surjective homomorphism determine? So it determines a closed embedding, closed immersion. From where to where? V to, so N, right? So this gives a closed immersion of the cone inside N and as schemes over W, right? Okay, so now suppose V is pure dimensional. What is the dimension of the cone of W inside V? If V is of dimension N, say, what is the dimension of the cone? So what does the cone do geometrically? What should the dimension be? The dimension has to be the same. Okay, so if it has the same dimension as V. Okay, so and V is pure dimensional. So okay, so if dimension V is equal to n, then the dimension of the cone is also n. Okay, so now so let S be the zero section of this pullback of the normal bundle. Okay, and now you have defined, so you know what the Gisin map S upper star is. Okay, I want you to apply it to the cycle associated to CWV. Okay, but so where will this happen? In which Chow group is this? Does this element lie? S upper star, where does it go from? From where to where? No, which scheme? W. Okay, but so CWV is a subscheme of N. So you have to see this cycle inside the Chow group of N. Okay, and then S upper star brings it to W. Okay, so this is an element of Chow group of W, but of what dimension? What is the rank of the normal bundle? NXY. So what is it? D. So what is the rank of N? N, the pullback. D. So what is the N minus D? Right, and so this is the definition of the intersection of X and V. Okay. Okay, so now, so this S upper star is the Gisin homomorphism that was, I believe, defined by Chetan. So it goes from A star N to A star minus D of W. Okay, this is the Gisin map. Okay, what happens to pi upper star of this? So pi is the projection from N to W. So what is pi upper star of this class? Class of the cone, right? So it's a unique class whose pullback by pi is the class of the cone. Okay, so that's also another way of defining it. Okay, so now, so we have to, so in Chetan's lectures, you did a lot of calculations involving Segre classes and Chern classes and so on and so forth, and you studied their functoriality with respect to push forwards, pullbacks, Segre classes of cones, Segre classes of subvarieties, which is defined as the Segre class of the cone of that subvariety or subscheme. Okay, so so the idea is that since this intersection product is defined in terms of these, so basically when you prove functoriality for Chern classes and Segre classes, it automatically gives you everything for the intersection product. Okay, but one has to be a little more precise. So okay, so let's do a small proposition. Just to connect to what the last calculation that Chetan did in his last lecture. Okay, so this intersection product is equal to, so now I'm going to write something. So this Cn is the total Chern class of the normal bundle. Okay, and then you cap it with the Segre class of W inside V. Now, since there is the total Chern class, there are pieces of various dimension in it, right, or various degree. Okay, so you have to just look at the degree n minus d piece. Okay, and then these two are equal. Okay, so this I'm doing it because just to put Chetan's computations into perspective. And so once you have a formula like this, so then all the functoriality properties will just follow directly because you have already proved them for these kind of classes. You already have functoriality for these guys, you already have functoriality for these guys, and you have projection formulas, etc. Okay, so then I don't have to keep on proving everything new for the intersection product. Okay, so how will we see this? Okay, so does somebody recall the last computation in Chetan's lecture? So it had something to do with the universal quotient bundle, right? Okay, so there is a universal exact sequence. So okay, let me yeah. So let us recall some notation. So let Q denote the projection. So okay, when we calculate capping by this class, the class that appears is the projective cone, right? So we have to do something about it. So take this. Okay, so let me write. Okay, so where? So I'll write C for CWV for brevity, and yeah. So this cone is over W. So you take this projective cone over W. So let Q denote the projection map. Okay. So now if you look at Q upper star of N direct sum this trivial bundle. So this canonically contains O minus 1, right? So this was the exact sequence, and there was a calculation with respect to this exact sequence in Chetan's talk, right? So all these are bundles over which scheme? W. Okay. So and the quotient is, so let's denote by xi the quotient. What? Oh yeah, everything is over, not over W. Everything is pulled back over PC plus 1. Sorry. So these are all. So this is as bundles on PC plus 1. Yeah. So there exists a short exact sequence. Yeah. Okay. So what was the calculation with respect to this exact sequence that you made? So if you take the top churn class of this, and if you cap it with the fundamental class of this cone, then you precisely get this. This was the calculation in Chetan's last lecture, right? So yeah, so this last week you did this. So x dot v is Q lower star of, yeah, I mean, of course you have to push it down on W. Yeah, so this cap of the top churn class with the fundamental class of C plus 1. Okay, do you remember such a calculation being done last week? Okay, so now, but if you have this, so now what can you say? Okay, so okay, I mean, writing this n minus d part and writing this formula is just for the sake of getting this nice expression. I mean, there's no, I mean, clever reason behind doing that really. So in fact, I can replace this this top churn class by the total churn class and actually just put the correct dimension part in the cap, which is n minus d. Okay, so this thing is equal to of the okay. So now what we are going to do is use the yeah. So Chetan also did one more property which said that the total churn classes, the total churn class and the total segre class are kind of inverses to each other. Right, in fact, that's how one was defined from the other. Okay, so now that you have an exact sequence like this, what does the Whitney formula give you? Is the product of the total churn classes of the sub and the quotient is the total churn class of the middle. Okay, so the Whitney formula gives you that. So the total churn class of xi and the product with total churn class of O minus 1 this is equal to the total Chern class of Q upper star n. I can forget the plus trivial part, right? Because you can, it's that thing is 1 in this case. Okay, so now, yeah, so what can I say about this total Chern class of Xi? So this is Chern class, total Chern class of Q upper star n times the Segre class of O minus 1, right? So x dot v, this is just Q lower star of total Chern class of Q upper star n times Segre class of O minus 1 cap with and this n minus d dimension part. Okay, so now all it remains is to use the projection formula, right? So what does the projection formula give you now? So the total Chern class of n times Q star times the Segre class okay, and now what is this expression? Well, I should put a cap here. That dot is not defined. So this was the projection formula for Chern classes, which was proved in either Amit or Chetan's lectures. So what is this? Haven't we gotten our answer back? So what is this expression? Isn't this the Segre class of the cone by definition? So this is just right, and this is by definition this S WV. Okay, fine with everybody, or there seemed to be some doubt? No, what happened?
This Segre class, that's what it should be minus. I mean, in our definition was C of O1 cup with D of C plus.
Yeah. But this is the Segre class, so it's the inverse. Yes. Okay, so now I leave it to you as an exercise. So what should happen if D is equal to 1? So D is equal to 1. So this is a regular embedding, but in particular it's also an effective Cartier divisor. So then you already knew a definition of intersecting with an effective Cartier divisor. So you should be able to check that the two agree. Right? So I leave this as an exercise. Okay? Okay, so yeah, so that's the formula, and now we come to the main construction, the so-called refine Gisin homomorphisms. Okay, so I will require something similar, but anyway, let me erase this. Okay. Okay, so again let I from x to y be a regular embedding of codimension B, and so let f from y prime to y be any morphism. Okay, so I'm just replacing v by y prime, just because I will, I need some functoriality properties. There will be a y double prime over y, and so just for notational reasons. No, let's see. Okay, and consider the pullback square. Yeah, so you have this y prime over y, you have this x, and then you form this x prime. So call this j and call this g. Yeah, so we want to define a pullback for this j, okay, in a sense. So we want to be able to go from Chow groups of y prime to Chow groups of x prime. And everything, we want everything to be determined by this regular embedding. Okay, so this I being the regular embedding has nice properties. The cone is a vector bundle and so on and so forth. Locally it is given by regular sequence. Very nice. But we want, and this J need not be a regular embedding. Okay, but we want to be able to make computations by, so actually if you see, all of Fulton's theory is basically based on making computations or reducing them to well-studied computations. So what will he generally do? So if you have to calculate, say, general intersection somewhere, okay, so you know how to intersect with Cartier divisors. So how to make something a Cartier divisor? Blow up. Okay, so then you want to go upstairs, and there you would be in a familiar situation where you know how to intersect Cartier divisors. But then to do computations there, you need to develop a theory which would handle these kind of situations. So which is why this morphism is always kept arbitrary. Okay, so that everything is geared towards, all the functoriality, etc. is, I mean, properties, compatibility properties are geared towards achieving this. Okay, so that is one thing to keep in mind while we are, and that's the motivation for trying to do things in this generality. Okay, so so we want to define. So let me call this I upper shriek. So in the beginning from cycles, so let's say Z n of y prime to a n minus d of x prime. Yeah, so define this by the formula. So I have to take yeah, okay, so take a cycle on n cycle on y prime, so which will have a formula of this kind, which will have an expression of this kind. So summation ni vi. So where would you send it? So what's the guess? So it's going to be ni x dot vi. Okay, so so these will be subvarieties here, the vi's. Okay, and then for that you have defined an intersection product with x. Okay. Okay, so so then you have this definition, and now I want to see that this passes through rational equivalence. Right, it's well defined and passes through rational equivalence. Okay, so one thing, where is x dot vi defined? Where was, in our first definition, where was x dot v defined? In x prime, so in w, right? So it's, so yeah, so it's defined inside x prime. Okay, so yeah, so yeah, that's fine. Now what I want to do is yeah, so I want to show that this passes through rational equivalence. Okay, so how will we show that? So this goes through the, so we have to just look at the definition that we had, right? So it's the Gizin pullback applied to the class of the cone. Okay, so in Chetan's lectures, he gave a construction using the specialization map, right? So what was it? Can somebody recall? So let me call the cone of, so I was calling this C inside, so for the cone of W inside V, so it's x prime inside y prime. So let me call this C prime. So this sits inside N, right? So which in our change definition is G upper star of N x y, right? So what is I upper shriek given by? So how is the, so it's given by the following composite. So you start with a cycle on y prime, then you take this specialization map and go into the cycle on C prime. So does somebody recall the definition of the specialization map? So how was the specialization map defined? So where does it take a subvariety, the class of a subvariety V? Yeah, so you take the intersection of V with x prime and then take the cone of that inside V. Okay, so this was, okay, so this was the specialization map. Okay, so now this C prime sits inside this N, so you can go inside Z little n of N, and now you can pass through rational equivalence and go into A n of N, and then this is a bundle over X prime, so then you have the Gisin pullback, right? So that you come back to A n of X prime. Okay. Now sigma passes through rational equivalence, right? This was also proved by Chetan. Okay, so the whole thing passes through rational equivalence, and so then this map factors through. This should be A n minus t. So A n of. Okay, so this is the map that we get. This is called the refined Gisin homomorphism. It's also denoted by I upper sheet. So you basically have this Gisin homomorphism. So if it is already at this level, then it's called the usual Gisin homomorphism. If it is for a pullback of this map, which need not be a regular embedding in general, so then it's the refined Gisin homomorphism. That's why the word refined. Okay, yeah. So okay, this is just a notational thing, but sometimes when it's the usual Gisin homomorphism, so if for instance if y prime equal to y and x equal to x prime is equal to x, then obviously, then this is sometimes all written by I upper star. Okay, so in books and papers without making any clarification. So just be careful about that. Whenever it's an I upper star, you should see what kind of a map I is, and then you would know what it is. Okay, so so now these refined Gisin homomorphisms have various nice functoriality properties, and they are all. I mean, you can see that everything is defined purely in terms of intersections. So, and for these intersections, you have this very nice formula, which in terms of the total Chern class and the Segre class. And for these, you have already proved all those functorialities. So it's just the proofs are just mechanical. Okay, so I'm not going to write down the proofs in detail, and because it's just pointless. You can all do it at home. It's just I'll just explain why the statements are so, and maybe say a few words about why such a thing should be, such a thing should be done or required. Okay, so so here are various compatibilities with push forwards and pullbacks. So so I'll just write property of upper streak. So suppose that we have okay, I'll just draw the diagram once, and suppose that we have a pullback diagram. Okay, so let me call this I prime, I double prime, P, Q, F, G. And so both these squares are pullback. Is the whole square also a pullback square then? Yeah, okay. So, and the only assumption at this point, any question? The only assumption at this point is that I is a regular embedding. Of codimension D. Okay, so now here are the properties. So if P is proper, okay, so then P is proper over here, and so if I start with a class on y upper prime, y double prime, so what you can do is you can push forward this class on y prime and then take the refined Gisin, which will take you here. Okay, so you can do you can do P upper star of alpha and then apply refined Gisin. Okay, so the claim is that this will be the same as refined Gisin applied to alpha and then Q lower star. So note that although this alpha is here, since the big diagram is also a pullback diagram, it has a refined Gisin. So a priori I should be distinguishing this I prime and I shriek and I shriek. But yeah, I'm not doing it. It will be just too difficult.
Suppose you had another, so let's say x0 and y0, and the map x0 from y prime to y0.
Something like this.
Y0 and also x0, right at the bit going down. And now there is, and yeah, this is I0, whatever.
Yeah.
And suppose J is the same.
Suppose J is the same.
Being the two fiber diagrams are the same.
Yeah.
Under these circumstances, is I0 of a sheet the same as I?
Is if I do you have these maps making it commute? No.
And
Then I don't
see
this.
the
Yeah.
maps are named I, not J. No,
Yes.
map is called I.
Yes. Yes. Yes.
It's called J of a sheet.
Yes.
Because it really depends on that data or not. That's the
Ha ha ha. So I believe it does, and I think even if yeah. So okay. Yes. Yes. It does. If they are of the same codimension, regular embeddings of the same codimension, then I believe this is true. But I have to check in Fulton. If not, I'll come to the situation because there will be a obvious disparity between the normal ranks of the normal bundles. So there will be something called excess intersection formula. So I believe if they are regular embeddings of the same, but I'm a little bit spooked because there's no connection between these two.
that's the point.
That's the point. Yes, yes, yes. So I believe it is. I think it is true if there is a diagram making it commute. So I think this is yeah. I think this is definitely true if there are maps from x0 to x and y0 to y making this also Cartesian diagram. But
So depend on the ambient space, right? If we attach the ambient space to y plus k1 and
you can do is y prime is contained in something smaller than y.
yes, yes, yes.
There it won't change.
There I believe it won't change. Yes, yes. If there is a map from this to
Because there is a purple coordinate.
yes, yes, yes. If there is a map from y0 to y, no connection. So I don't think this is true. But I example, yeah. Perhaps in the discussion session. I'm pretty sure Fulton would have mentioned a lot of examples without telling that it's supposed to be an example of this kind of a thing. So one will just have to search through it. This is my feeling. If at all it is false, there will be an example because that's.
codimensions are different, then of course this cannot be same. Like
No, if the codimensions are different, yes, yes, it cannot be the same. Actually, it will not be the same even if there are maps making everything commute and pull back everything. Even then, it will not be the same because there will be a disparity in the rank of the normal bundle, right? One will be of rank D, one will be of rank D prime. So just
The name you gave it was I of a sheet
yes,
for a good reason.
for yeah. Anyways, I think we will talk about the situation when this is x double prime, y double prime, and this is x prime, y prime, and everything happens in a Cartesian square. Yeah. So if there is no relation, I don't know. But I believe it should not be true. That's yeah. Okay. So this is the thing. The second thing is if P is flat. Okay. So where will this equality take place? A star minus D, right? X double x prime. But there will be a minus D because of the. So if P is flat of relative dimension, say R, okay, and then again alpha is in A star of Y double prime. So yeah, so you have the same. No, I think I should take. So I should take alpha in Y prime. So alpha in A star of y prime, otherwise I cannot pull back. So so you first, where is the diagram is here, yeah. So you first pull back and then apply I upper shriek is the same as first applying I upper shriek, then pull back. Okay, so if P is proper, Q is also proper. If P is flat, Q is also flat. Yeah, that is, yeah. And where does this equality take place? Or what dimension? Chow group? Star plus R minus D. X. Okay, yeah, so if I and I prime are regular embeddings of the same codimension, then what will happen? So okay, these two are going to be straightforward from the functorialities for these people. Okay, so if I and I prime are both regular embeddings of the same codimension, that is the that is exactly the thing. But why? Can somebody tell me what happens? So there should be a statement about normal bundles. Can somebody give me that statement? What is the statement about normal bundles? So there are two. Pullback of the normal bundle is the normal bundle. Why?
Because after it was injected,
Same rank. Okay, so if I prime is a regular embedding of codimension D, so then I just write the whole thing. So then basically the pullback of the normal bundle of I, this is isomorphic to the normal bundle of I prime, and hence so the refined Gisin are the same. Okay, so yeah, so this is inside. So if so, I have to start alpha inside A star of y double prime, and then this will happen inside star minus D of x double prime. Okay. Okay, so now comes to the next situation where the codimensions are different. Okay, so if I star I prime is a regular embedding of codimension D prime, which need not be the same as D. Okay, so now there is a difference between this, right? Because this is of rank D prime, this is of rank D. Okay, so you can, but this sits inside that. So you can take the quotient, and this is called the excess normal bundle. Okay, so yeah. So E, which is defined to be the quotient of. So in fact, I should have written this the other way around, right? So this normal bundle sits inside this one, right? So okay, so this is called the excess normal bundle. So what is this? The invariant of this lower square. Okay, so it's attached to the pullback square. Okay, so now what is the rank of this? Is the difference, right? So this is D minus D prime. So let's call this E. Okay, so now so this is a normal bundle on X prime, and now the statement is the so-called excess intersection formula. So which says, which tells you how much this I upper shriek of alpha and I prime upper shriek of alpha differ by. And what will they differ by? What will the intuition say? So where does this class lie? Okay, so we start with an alpha inside A. So this alpha is in A star of, let's say, y double prime. Okay, y. So where does I prime upper shriek lie? N minus d prime, right? I mean star minus d prime, and this one star minus d. So what's the difference? E, right? So basically you have to get the dimension down by E. So it will be the top churn class of the capping by top churn class of the E. Okay, so anyway, I will not prove this. So, but anyway, yeah. Okay, so then there are further functoriality statements. In fact, the chapter of Fulton is full of these functorialities. But anyway, so I'll just mention one more. Okay, so suppose you want to, so suppose there are two embeddings, I and J, and you want to check commutativity of the refined Gisin homomorphisms. Okay, so what is the setup going to be like? So you have a diagram like this, but in addition you have another. Okay, so let me, I don't know, there are no good names. Let me give S and T, and let me call this J, and let this is also a regular embedding. Okay, so let J be a regular embedding of codimension. D is taken, E is taken, F cannot be taken. So let's say D double prime. Okay, so now okay, so so let us see what does I upper shriek do and what does J upper shriek do, and suppose that all these diagrams are.
Sorry, I thought you only have changed F to a regular embedding, right? In your lower square. Why are you doing anything with the upper square? Right in the beginning of your.
You could see, for instance, you could take.
In the refined Gisin.
Yes.
I was a regular embedding.
Yes.
And F was I.
Yes.
I thought the question is what F also is a regular embedding.
Yeah.
And then you will begin with that diagram, not this.
Yeah, but that will be a special case of this, I believe. No, F can be a regular embedding, but the point is.
In which case one can do the refined Gisin for F.
One can.
Produce X intersection Y.
So then you'll have to produce from here to here.
See, after all, that would have been the simplest constant situation. This having a more general F is obviously a generalization of that, right?
Yes. That is correct. And
regular embeddings you want to intersect. Now you might do it treating this refined Gisin or treating that.
Refined Gisin, and I think and then answer will be the same.
So I thought
yeah. So then. Okay, so before going to the general one, let us do this one. But this is also true. What Jin said. So yeah. So if F is a do I require it to be of the? Now I'm just worried about the code dimension. If I have to assume that it's of the same code. So Okay, so you start with an alpha here. You first apply I upper shriek. You come here, and then the dimension drops by D. And then you come from here to here, and then the dimension drops by the codimension of this embedding. And the other way around. Huh? No, we are talking about so this, suppose F is a regular embedding. Okay, so using I upper shriek, I got a class from here to here. I don't want to push down, I want to use the Gizin. But the thing is that, see, there is a problem, right? So the Gizin, so this map is from this direction. How can it go from here to here? The Gizin has to go from here to here.
No, then X prime is already a close-up scheme of Y, and it will be happening in the
Yes.
There is nothing refined about this, just easy.
Yeah, there is nothing refined. This is just standard Gizin, and but so here's the question, right? So you start with an alpha here, then you have I upper shriek of alpha here, okay? And now where does J upper shriek send this? Chow group of where?
On the other hand, you take the Gizin F upper shriek and apply it to X.
I see. That's what you meant. Oh, no.
It will be the same.
Yeah, those two will be the same. Yes. If F is also a regular embedding, then this will be the same, and I just have to worry about the dimensions. Yes, of course. No, let us first write the statement.
It's going to produce like the next one.
Yeah, but
And that's the same cycle. It's not like this same class. Then starts with X, the other starts with Y and applies I. Starts from X and applies X.
See, you apply this I upper shriek, and then you will land inside A star minus D of X prime. Okay. Now the thing is to apply F upper shriek to the fundamental class of not.
You apply to something else, not to thing.
No, wait. Let me just figure out what the thing.
Work with the fundamental classes.
Yeah. So I want to.
Apply F upper shriek to the fundamental class of X, or apply I upper shriek to the fundamental class of Y.
yeah,
These are the two things you have to compare.
Yeah. So then it has to be. So I believe this seems to be this is the statement that you want. So for this, see, F takes classes here to classes here, right? F upper shriek.
Except you interchange
Of course. But let us see if this lies in the correct dimension. So I upper shriek, it definitely does. I upper shriek of Y prime, okay, it starts with dimension Y and it does, and F is a regular embedding, so this does as well. Yeah, correct. So, yeah.
So this equality is part of your compatibility.
Yeah, this is part of compatibility. I believe this was going to come later, but yeah. Anyway, the another this thing that I wanted to talk about was this. I wanted to talk about commutativity in the sense that if there are two Gizins, when is I upper shriek, J upper shriek equal to J upper shriek, I upper shriek? This is what I wanted to talk about. So if you have a diagram of this type, where everything is Cartesian, okay, so then you can see J upper shriek, it will take classes from here to here, right? And then you put I upper shriek, it will take here. And then I upper shriek, J upper shriek. So I upper shriek starts from here, goes here, and then J upper shriek takes it here. So then both the things can be compared over here, and there they are the same. This was the thing. This is another compatibility that I have to write. Okay, so the next one is exactly what I said. So then this J upper shriek, I upper shriek is equal to I upper shriek, J upper shriek as maps from A star of Y prime to A. Now star minus D double prime. Okay, so you can all do this. I'm not going to spend too much more time now. But what I will do is that, so one of the advantages of this Fulton theory is that this notion of Giesens is not just, whatever, so the slogan is that whatever works for regular embeddings also works for slightly more general morphisms, which are called LCI morphisms, morphisms of local complete intersection. Okay, and that is what I'm going to do, and then I'm going to stop. Okay, so what is when do you say that a morphism is of local complete intersection? Has anybody seen the definition before? Last week was there a definition?
I remember last week. Composite of
That probably we discussed, not they. Yeah. Okay. So the definition is LCI. Okay, so the slogan is that everything that works for regular embeddings works for LCI morphisms. What are LCI morphisms? So is said to be of a local complete intersection morphism. I'll just write this whole name once. If it factors as pi, so where so it factors as a regular embedding followed by a smooth morphism. Okay, so where
So your definition is not local on X, it is only local on Y.
Yes. So there are several definitions. So Fulton also mentions the definition which is which says locally this happens, but then he does everything for these because he says that this is what you see. There are some sort of issues in that. I don't know. I mean, the thing is doesn't make
predictive has a problem. Not being local.
Yeah. Okay. Yeah. Same thing. So anyway, so the more workable definition is so smooth morphisms. The smooth morphisms locally have a nice structure. So locally they can be factored as étal followed by just projection from an affine space. Okay, and this is exactly what happens in topology, right? So for manifolds, right? So this is what did you call standard normal form for submersion. Yeah, so this factorization is global according to Fulton, the convention in Fulton's book. But he also mentions that some people just require this condition to be local. So it doesn't matter the condition which I am going to give and which, I'll give an equivalent condition which is local anyway. So, both the things agree. But for him, he's not wanting this extra. Probably everything works even with the definition that this happens locally on X. But then probably there is a lot more to check.
Then there is no P.
There are different P's and then there is a, so what Fulton, so of course the definition is going to involve this I and pi. And then there will be results of the sort that the factorization does not matter. Even for this. So for these kind of checks will become really difficult if you allow local this thing, because locally also I and pi will vary, and then you have to keep track of how everything is compatible. So my guess is that this is why Fulton chose this global definition, because it's simpler to handle. So where I is a embedding and pi is a smooth morphism.
No.
At this point, no. This is just a definition which is global. Well, nice results are only for smooth projective varieties later. So in the whole theory, the theory is set up, nothing is required. But by the way, okay, so one thing is that now you have all this theory. I mean, this is the point that Srinivas was making, I think, yesterday. So you have all this theory, and you know that the intersection multiplicity is, I mean, how it is determined, right? So there are, I think, so Chetan in last week connected Segre classes to multiplicities coming from Hilbert polynomial, which are computed using the top coefficient of the Hilbert polynomial. And in my previous lectures, I gave a definition of multiplicity using the Tor formula. It's a commutative algebra theorem that all these multiplicities agree. So ultimately, you know that, I mean, everything is the same, but whatever I did was only for smooth projective varieties. Okay, so for smooth projective varieties, what is classically done and what Fulton has done is everything is consistent. Okay, so you know this, I mean, post facto. You did not know this previously, only because the theory that is cooked up is consistent and calculates everything as expected is, yeah, the thing. But okay, what was I going to do? I was going to give another slightly more workable definition, but yeah, see that if you have to make, so if you have to make local calculations, then this is usually not very helpful. But if you have to prove some functoriality properties and so on and so forth, then this is very helpful. Okay, so there are two ways. So equivalently, yeah, F is LCI if X is covered by open subschemes yeah, well, I'll just write U, I will not write UI. Okay, so open subschemes U for which F restricted to U from U to Y factors as, so this, yeah, so U to some an of Y to Y, and this is projection onto Y, and so this IU is a regular embedding. Yeah. So so there is a problem. So the thing is that no.
That's why he wants lower.
That's why, yes.
Lower assumption type multiplicative, then you can take it to a relative.
Yes. You are right actually. So if I make this definition local, then these two are equivalent. Okay. So if I say,
You are using the weaker one.
yeah. So let me write in particular, or this implies. Okay, so this is correct. So, but do you understand that? Okay, so let me just very quickly say, if you made this definition local, in the sense that you would say that X is covered by open subschemes U, such that F restricted to U factors like this, then the two definitions are the same. Okay, so and why is that? Because smooth morphisms can always be factored as something ethyl followed by projection of this form. Okay, so this is completely parallel to the manifolds story, right? So this is a standard normal form for submersions or something. Yeah. So anyway, so that you can do, but then how do you take care of the ethyl part? So ethyl maps can locally be made standard ethyl. Okay, so standard ethyl are maps which are factoring from A1 over this thing. So just look it up. I'm not going to write this down in detail. Huh? No, you don't require Zariski's main theorem. Just ethyl map can be locally factored into standard ethyl. So it will be it will be an immersion inside some A1 followed by this thing, and then the whole thing you have to write down and see. That is, I mean, it just gives you a projection from AN over some A1 over this to Y. You might have to go to a high.
It's like primitive element theorem.
Yes. Yes.
But now you want it to work over rings.
Yes.
It might need something like that. No, it's just you already got the condition that you said that.
Maybe assume that everything is over a field.
I mean, you can always reduce to the case where you're adding one element at a time. So
Yes.
instead of A1, you will have some A1.
Yeah. That's what I mean. Yeah. So you will have to go to a higher affine space, but then it will still be true. This is the claim. Anyway, but let's check this later maybe. Okay. So yeah. So now how can you extend the definition of refined Gisin morphisms to an LCI morphism? So you know the definition for I, right? And you want to define F upper Schrick. Okay, so how will you define? So there is only, I mean, one clear way, right? But you have the upper star.
That's what he wants you to.
Huh?
He's asking you a speed vector question.
Yeah, exactly. Yeah. But then there is one thing that you have to check. If there is another factorization, right? Why would the two agree? A, B, C, D, E, F. Use all those. Yes. So use all those and then check that this is independent of the factorization. Okay, so suppose that this is a pullback square. Okay, so H. Okay, maybe F prime. G, H. Okay, so suppose this is a pullback square and F is LCI, and suppose that F is so first you apply I and then you apply pi. Okay, so suppose that I is of its regular embedding of codimension D, and then this pi is I require a relative dimension here, right? So suppose that the relative dimension is okay, so relative dimension E. So then I want to define F upper Schrick as I upper Schrick composed of pi upper star.
So pi upper star in finding the smooth morphism is flat, so you define the pi. So why don't you insist to this smooth? Why don't you just take it as a flat in your definition of local intersection?
So I think it is of different importance. I think from the relation with the cotangent complex. So this, so this is of relevance of in some other way. So this is the reason. So no. Why didn't you assume that? So for the definition, you only required this to be flat. Why did you assume smooth? No, the point of LCI morphisms is that you can make sense of what is called a virtual tangent bundle and so on and so forth. But I think the expert is in the first row. Yeah. No, this is important for some other. So these morphisms are important for the theory in another context, which is why you are, I mean, Fulton is trying to define Gizin for these guys. How?
Because see, even if you have a box to Y, let me give you a simplest example. Take Y.
Yeah, of course.
When Y is spec K, everything is flat. But if it is smooth, it's completely different. If your demand of etc. For example, the case to think about is that suppose X and Y are smooth. I'm saying Y equal to spec K is good enough to answer this question. No, but I'm saying if you look at X and Y to be smooth, when you see that it is LCI, or it's any morphism is LCI.
Any smooth morphism or map.
Any morphism. Take the product.
Graph will be a regular. Graph will be a regular embedding. So if the variety is smooth, right? Yeah. So any morphism between smooth varieties is LCI because of the graph. Yeah. Right. Yeah. So did everybody get the comment? So if you have a morphism between two smooth varieties, you can factor it as the graph. X goes to x cross y as the graph. Little x goes to little x comma fx, kind of, but written properly in algebraic geometric way. And then the projection. Okay, so the first one will be a regular embedding of codimension equal to dimension of which one? Why? And I mean, it should have the same dimension as x, right? So the codimension will be the dimension of y, and then the projection should be smooth. Okay, so okay. So verify that this is well defined. So that means it's independent of the factorization. Okay, so now I think it's already time to end. So what's a good place to end? Just record for the fact that we really have a product structure on the chow ring this way also, and you already know, right, what is to be done. See, we had to work very hard using moving lemmas, etc. to define this thing, but now here, well, you already know, right, using the exterior product and the diagonal. So what's the definition going to be? So let X be a smooth. By the way, I'm saying variety all the time, but really variety is not required in any of this theory, right? So it's smooth scheme. So that's also a generalization in which, okay, so let's say of dimension D over a field. Huh? No, its irreducible components will be connected components. You can work, but to make statements, you can do it in. By the way, it's clear, right? Smooth schemes, irreducible components are connected components. What's the commutative algebra theorem which gives this? A regular local ring is a domain, right? So the analog of this, the interpretation of this is that in smooth schemes, irreducible components are connected components. What will happen if two irreducible components intersect? Yeah, so this condition will be violated. So at the intersection points, the local ring cannot be smooth, regular.
Since you are taking smooth under product, it's okay. Variety product may fail to be
irreducible. Yeah, over an arbitrary field. We have already seen many times the example of C tensor C over R. Okay. Yeah, so smooth scheme of dimension D, and then the diagonal. So is a regular embedding. Of codimension D, and then the intersection product on the chow, well, okay, X is defined by Okay, so where does it, so we'll just keep track of where this goes. So it's going to be defined from AMX tensor ANX. So this will go by exterior product inside AM plus N of X cross X. And so this is the exterior product. And then I will get it down to M plus N minus D of X. And what is the map? Delta upper, yeah, which is the same as delta upper star, as I explained. I mean, if the refined notation is used in many cases, but actually, yeah, so people will write delta upper star and work with it, but you should not be confused, because it's not, obviously not a flat map, right? So they actually mean the Gisin map. Okay, so now you have the product, and okay, of course, check that if you write this thing, I mean, if you grade everything by codimension, then the codimensions will be preserved, right? I mean, so what will happen to codimensions? They will be added, that's what I mean. So can you see that? So this, if you just grade everything by codimension, so this A lower MD will be A upper D minus MD. Then you will see that the codimensions actually add. Okay, so that's why, I mean, it's more natural, because the same thing happens in cohomology as well. Okay, so that's a good point to stop. Thank you for your attention.